Alright, so what we're going to look at here in topic 8 is the mighty regression analysis, which we do via a special kind of graph called scatter plots. And scatter plots are quite simple to produce using Minitab or Microsoft Excel in this case. And what they show are the relatedness between variables which are paired in some way. On this opening screen, what I've done is generate a scatter plot which shows the comparative stream flow in the Yarra River at Warrandyte and Templestowe at the same time. So if you remember back to that data set, which was Yarra stream flow, we had a whole lot of paired data points where a stream flow measurement was taken at Templestowe and at Warrandyte at the same time, and allowed us to directly compare how the stream flows may differ between those 2 points along the Yarra River. And so what this scatter plot has done is just plot what the corresponding stream flow is in Templestowe at a certain point in Warrandyte. And when two variables change in a consistent way, we get the interesting distributions displayed in the scatter plot. Here it looks like we have a nice linear straight line where it appears that as the stream flow increases at Warrandyte, the stream flow at Templestowe in kind also increases. And I've put on a line of best fit, which we'll see how we generate over the top of that, which sort of shows sort of the average change in Templestowe as Warrandyte changes. So the average distribution of this scatter plot. So we'll explore now how we use these scatter plots to develop things called regressions. How we, from these regressions, we can work out, make statistical models to explain the change in one variable in relation to another, and we can see how we can measure test the significance of the relationship between within these regressions. So the first thing to do is download the datasheet student beer consumption. Download the one for Yarra Streamflow version 2 at the same time. Both of these are found, I believe, in the Topic 8 folder on the subject page. In this student beer consumption, the first example that we'll go through, what we have is a data set where a study was done where students at a party were asked how many beers they consumed, and then their blood alcohol content was measured. And we want to see if we can work out a relationship between beers consumed and blood alcohol content. How can we do this using inferential statistics? Well, we can't use Z distributions. We can't use T distributions. We have to use this special kind of inferential statistic called the regression. So here we have the same data that's in that Excel spreadsheet on the slide, and we have 3 columns of data, just a code given to the student. That's in column 1, column A I should say, numbered 1 to 14. We have the beers that each of those students respectively consumed, ranging from, what was that, 1 beer up to 8, and then their corresponding blood alcohol content. And then the scatter plot derived from this data set is found here in the right. The explanatory variables put in the x-axis, so that's the treatment, and in this case the treatment is beers consumed. In the y-axis we put the response variable, in this case it's the blood alcohol content of the student. So for example, the student that had 1 beer had a blood alcohol content of 0.01, so in the 1 above 1 in the explanatory variable 1 for the number of beers, we put a dot where it corresponds to 0.01, and so on and so forth. We do that for each of the data points, and you can see, hopefully you can see, that there's actually a nice linear sort of relationship building there, where the number of beers consumed increases the blood alcohol content consistently of the student. Interpreting a scatter plot is simple. First of all, we look at the pattern in the data. So in that blood alcohol content example, look like a linear or sort of straight line in the data. Others are curved. Others we find clusters where there's a bunch of dots down the bottom, and then there's another bunch of dots elsewhere on the distribution. And some there's no pattern at all, where there's just no... The change in one variable has no effect on the change in the other variable. There's positive scatter plots where an increase in one variable leads to an increase in the other. A negative correlation means when there's an increase in one variable, there's a decrease in the other variable. So it will be a line pointing down. And then there's those with no direction at all, and we'll see an example of that. They're just dots all over the place. So we look at the form, we look at the direction, and then we look at the strength of the relationship. Do the dots follow really closely that line of best fit, or are they sort of dotted all around the line? That strength we actually measure with a special parameter called R squared. And then we look for outliers. Outliers in regressions are really interesting because they tell us about extraordinary circumstances. So we don't get disappointed by outliers, so dots which don't fit a nice pattern. We find them interesting and we try and explore why they're out like that. And a good example is that first slide where there's a bunch of dots outside the tight line. And we'd ask ourselves, what about the hydrology of the Yarra leads to this bump in the regression? Okay, so we have, as promised, some different patterns in regressions. The top left, and let's talk about these four in a sort of larger square on the left-hand side. The top left, we have a negative linear relationship. Top right, we have a positive linear relationship. So as the x-axis increases, so does the y-axis. And then the bottom left, bottom right, we have two non-linear relationships. One, we have a sort of a curve, an exponential curve. As x gets bigger, y rapidly becomes larger. And then we have a sort of parabolic relationship in the bottom right. And then these two on the far right, we have no relationship at all. One is just flat lines. So as the x-axis increases, the y-axis doesn't do anything. And in the bottom right, when x increases, we just have the y just goes all over the place. Sometimes it increases, sometimes it decreases. There's no pattern there that we can discern. As important as the form of the regression is, as equally as important as that is the strength of the relationship. How tightly do our data points follow the pattern that we can see? In the left-hand one here, we have a very strong relationship between one variable and the other. Quite tightly, as the x-axis increases, so does the y-axis. On the right-hand side, we've got a weaker relationship between the two variables. As x increases, y does increase, but there's a lot of variation in the data points. Sometimes it doesn't increase as much as another data point. Right, so there's a fair bit of error in that relationship. Whereas on the left-hand side, it's very, very tight. They consistently increase with each other. So the tightness of the fit of our points to the distribution is given by the correlation coefficient known as R, or Pearson's R. Pearson's R varies from -1 through to 1. -1 is a perfect negative linear relationship. So a perfect straight line going down. An R of +1 is the perfect line going up. Every point fits that distribution perfectly. So the higher or the closer R is to 1 or -1, the closer our points fit a perfect straight line. Whether or not it's positive or negative tells us whether or not it's a negative or positive relationship between the two variables. So we'll look at how we derive R and how we use R, and it's remarkably simple, especially with the benefit of Microsoft Excel. So here we see how R changes from in scatter plots where there's no similarity between the two variables to ones where they change in exactly the same manner. Top left, we have an R of 0. There's just no pattern in the data whatsoever. As the x-axis changes, the y just does whatever it wants. When we get to R of 0.3, we can sort of start seeing a trend emerging. That one looking like a negative trend, and that negative 0.3. R of 0.5, all of a sudden we start seeing that trend emerging a lot more clearly. That's a positive trend there, so pointing upwards. 0.7, we're getting quite a strong trend. This one's negative 0.7, it's pointing downwards, but we can clearly see the linear trend. And then when we get into 0.9 and 0.99, all of a sudden the data resembles a line itself. There's some rules of thumb with regressions that allow us to judge the power of the association shown in our scatter plot. When R is 1, we've got a super strong linear association. If it's between 0.5 and 0.75, we've got a moderately strong association between the variables. 0.25 to 5, a weak association. R of 0, no association. And that works both with positive R's and negative R's. We'll, however, be using Pearson's R table to work out whether or not our R is above a minimum value required for to say that there is a significant relationship between two variables. You'll find Pearson's R in the formulas and tables file. Near the bottom is the Pearson's R table, and you simply get the sample size, so the number of pairwise associations that you're putting in your scatter plot. So say 20, you go down to the 20 line and then work away to the right until you find the desired level of confidence. Note the confidence is given as the upper tail probability only, so we're looking at both tails, so you have to multiply that number there by 2. So if you see 0.025, multiply that by 2, and that gives you the 0.05. So you work across from, say, the sample size is 20, you work across the table until it lines up with the 0.05, pardon me, and that provides the value of R as a minimum, which represents a significant relationship. So if your R is greater than that number, you have a significant relationship. So the formula for calculating R looks really nasty, but it's a lot easier than it looks. It's simply a combination of the average difference between each data point from variable 1 and variable 2, here labelled X and Y, and their respective means. So we have the sum of X minus the mean of X, Y minus the mean of Y for each data point, divided by the standard deviation of each of those data sets. So if you have a data set and you know the sample size, you can calculate R. So it's simply the sum of each X value minus the mean divided by the standard deviation times each Y data point minus the mean divided by the standard deviation. So R is a function of the size of the standard deviation as well as the size of the sample size. R often, when it's calculated by hand, is the second formula there is used. It's the sum of X times Y, so each variable 1 times variable 2 for each data point, minus the sample size times the mean of X and the mean of Y divided by the sample size minus 1 times the 2 standard deviations. So it looks a little bit nicer that way, and it's quite simple to calculate, especially with Excel, and can be done traditionally by hand. Although for this subject we'll always get R calculated for us, but you need to remember what is given to you in the exam. But if you're asked a question, if the standard deviation drops, why does R increase? That's because each of the functions, or the sum function, as part of it, the numbers are divided by the standard deviation. So as they drop, those numbers get bigger. So the lower the standard deviation, the better our R. So here it shows the old way for calculating R, Again, we'll be using Excel and I'll be demonstrating that at the end of this presentation, how quickly you can generate R using Microsoft Excel. But here, using the manual method, the correlation between the regression analysis of beers consumed versus blood alcohol content gives an R of 0.871. So the relationship between blood alcohol content and beers consumed in this study gives an R of 0.871. So we consider that a strong positive linear association. So there's a strong relationship between beers consumed and blood alcohol content. So I should correct myself at this point. When we're looking at the relationship between two variables on a scatter plot and we're saying, oh, it looks like a pretty strong relationship and it's positive or it's negative, it's linear or it's curved, that's called correlation analysis. We're looking at a correlation between one variable and another. We can extend this using the same techniques to regression analysis, where we fit a mathematical model to the relationship between one variable and another. So we can actually get a mathematical function that explains how one variable changes as the other one changes. Let's see how simple this is. All right, let's look at a simple study here and how we can derive a mathematical model to explain two variables. We have the mating calls of this tree frog. And what they did was they got 17 frogs and they wanted to work out whether or not their frequency that they provide this mating call is altered by the temperature of the air. So they monitored 17 frogs, looked at the temperature and measured the number of times they did their mating call. Alright, so they've got two sets of data, the temperature and the number of mating calls. So what we want to know is, can we create a model such that if we're given the temperature of any given day, we could predict with a certain level of confidence the call frequency of these frogs. And we can do this via a simple scatter plot. In fact, it's the equation which describes this line of best fit which goes through the middle of our points. The equation of that line actually provides the model that explains how one variable alters with the other variable. Let's see how we can derive this. So on that previous slide there was a bit of information on that graph. It said R was about 0.871. So that means there's a strong relationship between temperature and mating call frequency. But then there was an equation, the equation which describes that line. And if you remember back to maths, the linear equations have a very specific structure, which is y equals ax plus b. So y, the value of the y-axis, is a times the value of x plus b. A represents the slope of the line, so how much does the line go up for every increase in one of the x-axis. And b is where the line meets the y-axis, it's the y-intercept. And we'll see this again on the next slide. But first of all, here was the equation for this relationship. So this, the line of best fit for that previous scatter plot was y equals 0.4014 times x minus 3.585. Therefore, if we plug a temperature into that equation, it will give us the predicted call frequency of the frogs. So in this case, it's 24 degrees. So we just put 24 in the place of x, solve for y, and we get that if it's 24 degrees, we predict that there will be 6 mating calls given by each frog. 0.4014 times 24 minus 3.585. Here's what I was saying before. So linear equations are given the formula y equals a plus bx. Sorry, I said ax plus b. It's a plus bx. At school, it's often given y equals mx plus c, but at tertiary level, we say y equals a plus bx. Even though I just said it was something different, but that's the form that we use, y equals a plus bx. A is where the line meets the y-axis, so when x equals 0. So if you put x equals 0, it's b times 0, which is 0, which just leaves a. So y equals a when x equals 0. And b is the slope of the line. So how much does y go up for every increase in x? Now this line isn't just put randomly through the points where it looks like it fits best. It is actually the line of best fit, and what it does, its role is to minimize the residual. Residual, denoted by the letter E, is when you get each data point subtracted by the mean. That is the residual. The predicted y from the equation, the difference between each value of y and that predicted by the equation. So what we want to do is come up with a line where the y that's predicted by the line and the actual point at that area on the scatter plot is the smallest. Right, so that was a really poor explanation, and it's explained a lot better on the slide. But the role of the line of best fit is to decrease the residual, the distance between the actual observed values and that predicted by the equation for the line. We can calculate A and B relatively simply. First of all, B is simply R times the standard deviation of y divided by the standard deviation of x, or the standard deviation of the data set used in the x-axis. So that's B, that's simple. A is simply the mean of y minus B times the mean of x. Simple. And that's our equation. Again, Excel will do it all for us. So calculating by hand, this is how we derive the equation for the blood alcohol content data set. R times the standard deviation of the explanatory variable divided by the standard deviation of the response variable. Sorry, the other way around. The standard deviation of the response variable divided by the standard deviation of the explanatory variable, or the variable in the y-axis divided by the standard deviation of the variable in the x-axis. And then the y-intercept, or A, is simply the mean of y minus B times the mean of x. And that gives us an equation 0.0008 plus 0.144x. So for every increase in beer, the blood alcohol content of the student increases by 0.0144. That is what is predicted by our model. Right, so the slope of the line dictates how much the y variable increases for every unit increase in the x-axis variable. So for every extra beer consumed in this case, the blood alcohol content goes up by about 0.0144. That is what is predicted by our model. But how good is our model? That is the question. Well, the question is, how good is the model that we've derived? Well, all these models come with one caveat. We don't use them for predicting values of y outside the range of the initial data set. So outside the range of values that we use to derive the model. And this blood alcohol content gives a good example of that, because the y-intercept as predicted by the equation is 0.0008. So that says even if you had no beers, 0 beers, your blood alcohol content will be 0.0008. That's not likely because you wouldn't have consumed any alcohol. Alright, so that's called extrapolation. When you're using a model to derive figures, make predictions outside the original data set. That's fraught with danger. A more sensible thing to do is interpolation, which is predicting values of y for values of x used to derive the data set, or within the bounds, or within the range of points used to derive the model itself. So we need to only use this model for beer consumption between 1 and 8 beers, because that was the range of x-axis variables that we used to derive the model. So first of all, we don't extrapolate using our models. The other caveat we use to tell how good our model is the R-squared value of our regression. R-squared is referred to as the coefficient of determination, and is simply our R value squared. So if we have an R of 0.7, our R squared is 0.49. And the definition of the R squared, what the R squared gives us, is the amount of variation in Y predicted by X. Right. So if we have a R squared of 0.49, that means about 50% of the variation we see in Y is explained by X. The other 50% of the variation in the Y variable is it has to be explained by other confounding variables. So with our blood alcohol content example, our R squared would be 0.871, which would be about 0.68. So about 68% of the variation observed in blood alcohol content can be explained by the beers consumed by the students. The other 32% is due to other reasons. So there's the danger of trying to do 0.871 squared in your head. 0.871 squared is actually 0.758. So about 76% of the variation in blood alcohol content in the students is explained by the beers that they consumed.